So today, what I want to tell you about is the Poisson point process, which is a continuous analog of the Bernoulli point process that we talked about earlier. As always, let's begin with the story. Suppose we have a tavern owner who models the intervals between customer arrivals as independent random variables with an exponential of rate 6 per hour distribution. What would be the chance of getting at least 2 customers in the first half hour? Consider a Bernoulli process. Remember there, B1, B2, etc. are IID Bernoulli random variables P, and they have an associated Bernoulli point process, which just counts all the values of I such that B sub I equals 1. Well, suppose that we wrote those elements of the Bernoulli point process in order. So B was T1, T2, etc., where T1 was less than T2, less than T3, represented all the places, all the indices where the Bernoulli had value 1. In that format, the time until the first I with B sub I equals 1 has a geometric distribution. So we could write T1 is geometrically distributed with parameter P. Then the time until the next I with B sub I equals 1 is also geometrically distributed. So T sub 2 minus T sub 1 also has a geometric with parameter P distribution. This idea gives another way to create a Bernoulli point process. Instead of using just Bernoulli random variables, use geometric random variables. So if we have an IID sequence G sub 1, G sub 2 of geometric random variables with parameter P, then if I just look at G sub 1 and then G sub 1 plus G sub 2, G sub 1 plus G sub 2 plus G sub 3, etc., those form a Bernoulli point process of rate P. So for instance, if the first geometric was 3, the second was 1, the third was 4, then the first point in the process would be 3, the first geometric. The next one would be 4, 3 plus 1. Then the next one would be 8, 4 plus 3 plus 1. That is, the point process starts off with points at 3, 4, and 8. And that means that the underlying Bernoulli process, B sub 1, B sub 2, has to start with 2 zeros followed by a 1 in the third spot, a 1 in the fourth spot, 3 more zeros, then a 1 in the eighth spot, and so on. So geometric random variables can be used to create a point process on the positive integers. But what if the goal is to create a point process on all real numbers from 0 up to infinity? Then a continuous analog of geometric random variables is needed. To understand what this continuous analog is all about, recall that G is geometric with parameter P means that for all I positive integers, the probability that G equals I is P times 1 minus P raised to the I minus 1 power. We're going to use the symbols that look kind of like square brackets with one side cut off to denote the ceiling of x, which means it's the function that rounds x up to the next highest integer. For example, the ceiling of 4.3 is 5 because we're rounding up to 5. The ceiling of 3 is just 3 because 3 is already an integer. The ceiling of negative 2.3 is we're rounding up to negative 2. Now, in order for the ceiling of x to equal an integer I, x must be strictly greater than I minus 1 and at most I. So in other words, the event that the ceiling of x equals I is the same as the event that x is greater than I minus 1 and less than or equal to I. Now suppose that u is a standard uniform random variable and p is a number from 0 up to 1. Then g, if it's the ceiling of the natural log of u divided by the natural log of 1 minus p, has a geometric distribution with parameter p. The proof works as follows. Let I be a positive integer and alpha equal the natural log of 1 minus p. Because p is a number between 0 and 1, this will be less than 0. Then the probability that g equals I equals the probability that natural log of u over alpha, the ceiling of that expression, equals I. We can write that as the probability that I minus 1 is strictly less than natural log of u over alpha, which is less than or equal to I. Inside the probability, we can multiply through by alpha to say that because alpha is negative, we have to switch the order of the inequalities, and the probability that I minus 1 times alpha is greater than natural log of u, is greater than or equal to I times alpha. Now, the inverse of the natural log function, the exponential function, is increasing, and so preserves the order of inequalities. So exponentiating inside the probability gives that the probability that g equals I is the probability that the exponential function applied to alpha times I minus 1 is greater than u, is greater than or equal to the exponential function applied to alpha I. The probability that a standard uniform is between two numbers, between 0 and 1, is the bigger number minus the smaller number. So this probability equals the exponential function applied to alpha times I minus 1 minus the exponential function applied to alpha I, which in turn, if we factor out the exponential function applied to alpha times I minus 1, leaves a factor of 1 minus the exponential function applied to alpha. Since alpha is the natural log of 1 minus p, which is less than 0, that means that the probability that g equals I will be 1 minus p raised to the I minus 1 power times the quantity 1 minus the quantity 1 minus p, which is just 1 minus p to the I minus 1 times p. Whew. That's just the probabilities associated with a geometric random variable, and the proof is complete. Note that negative the natural log of a uniform, or natural log of 1 over that uniform, has the distribution called the standard exponential distribution. Moreover, natural log of 1 over u divided by lambda has an exponential distribution with rate lambda, and we write that as natural log of 1 over u divided by lambda has the exp for exponential distribution with rate lambda. So the exponential distribution is the continuous analog of the geometric distribution, with lambda equaling negative the natural log of 1 minus p. So how can we use exponentials to create a Poisson point process? If IID geometric random variables, g sub 1, g sub 2, g sub 3, with parameter p are summed to give point values, the result is a Bernoulli point process with parameter p. So what we're going to do is take IID exponentials, a1, a2, etc., with rate lambda, and sum those to give point values. The result is a Poisson point process with rate lambda. And that's our definition. Let I1, A2, etc. be IID exponential with rate lambda. Then the set P that consists of A1, A1 plus A2, A1 plus A2 plus A3, etc. is a Poisson point process on the interval from 0 up to infinity of rate lambda. We write P has a Poisson point process distribution with parameter lambda. With the Bernoulli point process of parameter P, there were 3 questions that needed to be answered. 1. What was the time until the first point? 2. What was the time until the rth point for some positive integer r? And 3. What is the number of points that fall into a set 1, 2, 3 up to n of integers? The answers to these 3 questions are as follows. Let b equal t sub 1, t sub 2, etc., with t sub 1 less than t sub 2, and so on, be a Bernoulli point process with parameter p over the positive integers. Then the time until the first point, t sub 1, has a geometric distribution with parameter p. The time until the rth point, t sub r, has a negative binomial distribution with parameters r and p. And the number of points in the set B intersected with the set of integers 1, 2, 3 up to n has a binomial distribution with parameters n and p. The same 3 questions can be asked for the Poisson point process, with a slight modification of the last question to deal with continuous state spaces. Number 1. What is the time until the first point? Number 2, what is the time until the rth point for some positive integer r? Number 3, what is the number of points that fall into the interval from 0 to t? The answer to the first question is that t sub 1 will have an exponential distribution with parameter lambda, because that is exactly how the Poisson point process over the interval from 0 to infinity is defined. For the second question, remember that t sub 1 is an exponential random variable. Then an independent exponential is added to t1 to get t2. Then another independent exponential is added to t2 to get t3, and so on. Hence, the value of the rth point will be the sum of r IID exponential random variables of rate lambda. The distribution of the sum of exponentials is given the name gamma. So, definition. Suppose that r is a positive integer and a sub 1 up through a sub r are IID exponential random variables with parameter lambda. Then t sub r, which is a sub 1 plus a sub 2 up through a sub r, has a gamma distribution with parameters r and lambda. And we write t sub r tilde gamma r and lambda. Now, it turns out it's customary to write out the word gamma in English when referring to this distribution rather than just using the Greek letter. Also, an alternate name for this distribution is Erlang, but that is mostly used in the operations research literature. Finally, consider the number of points that fall into the interval from 0 up to t. This will be a random variable that comes from the Poisson family of distributions. Say that a random variable x has the Poisson distribution with parameter mu if the probability that x equals I is the exponential function of negative mu times mu to the ith power divided by I factorial times the indicator that I is a non-negative integer. Those familiar with the Taylor series expansion of the exponential function as 1 plus x squared over 2 factorial plus x3 over 3 factorial, etc., might note that the probability that x equals I is the ith, starting with 0, term in the expansion of the exponential of mu. So by multiplying all terms by exponential of negative mu, the probabilities will add up to 1. The number of points in a Poisson point process that fall into an interval from A to B will have a Poisson distribution, with parameter equal to the Lebesgue measure of that interval times the rate of the Poisson point process. Let P, which is T1, T2, etc., with T1 less than T2, and so on, be a Poisson point process of rate lambda over the interval from 0 up to infinity. Then for any A less than B, the time of the first point, t sub 1, will have an exponential distribution with parameter lambda. The time of the rth point will have a gamma distribution with parameters r and lambda. And the number of points that fall in the interval from A to B inclusive will be Poisson distributed with parameter b minus a quantity times lambda. Unlike the binomial distribution, a Poisson distribution only has one parameter. So the single parameter for the Poisson is the Lebesgue measure of the interval times the rate of the process to give Poisson with one parameter, lambda times the Lebesgue measure of the interval from A to B. Whereas for the Bernoulli point process, the parameters are separate. It's going to be binomial with the number of elements in the set from 1 up through n. So we're using counting measure instead of Lebesgue measure, and then comma p. P has to be a separate parameter. Now the last distribution can be used to solve the tavern problem at the beginning of this lecture. For a Poisson point process of rate 6 per hour, the number of points of the process that fall in the interval from 0 to 1/2 hours will be Poisson distributed, with parameter quantity 1/2 minus 0, the length of the interval, times 6, which is just 3. Note that the units of hours and per hours cancels out. The question is asking then, what is the chance that if x is Poisson distributed with parameter 3, that it is at least 2? Now the negation is a bit easier to work with here. The probability that x is at least 2 is 1 minus the probability that x is at most 1, or 1 minus the probability that x equals 0 minus the probability that x equals 1. This is just 1 minus the exponential of -3 times the quantity 1 to the first power divided by 1 factorial plus 3 to the first power divided by 1 factorial, which comes out to be 0.8008, etc. Here's another example. Suppose that P is a Poisson point process of rate 2.1. What is the probability that the number of points in P that fall into the interval from 2 to 3 equals 2? Well, if we let capital X be the number of points of P that fall into 2 to 3, then from the last fact it holds that X has a Poisson distribution with parameter 2.1 times 3 minus 2, which is just 2.1. So the probability that X equals 2 will, from our formula for the distribution of the Poisson, have probability exponential -2.1 times 2.1 squared divided by 2 factorial, which is about 0.2700. Now, another useful fact that is if we have two intervals a to b and c to d that do not overlap, so a is less than b, which is less than or equal to c, which is less than d. Okay, they can overlap at one point, but they mostly do not overlap. Then the number of points that fall into these two intervals are going to be independent. Formally, we say that if P is a Poisson point process of parameter lambda for A less than B, less than or equal to C, less than D, if we let n sub interval from A to B be the number of points that fall into the interval from A to B, and n sub CD be the number of points that fall into the interval from C to D, then n sub interval from A to B and n sub interval from C to D are independent random variables. And again, note that there can be overlap between the intervals from A to B and C to D at one point. That is because the chance that a particular point will be in the Poisson point process is 0. So that's how we deal with the Poisson point process. Instead of having a geometric amount of time between points, we have an exponential amount of time, which can be a continuous random variable. See you next time.